Hello all! So someone had kind of mentioned that they wanted me to go through ligands and oxidation and geometry because they felt that how it was explained in the lecture did not really help them to understand the concepts that well. So I thought, oh, okay, well, I'll go through them. And also another student pointed out to me that if I go through them, then it's going to help me to save time on answering emails because you guys already have this as your resource. So I'm going to quickly go through a couple of problems that deal with ligands and oxidation and geometry and kind of relate them to an overarching theme, that you're going to see when you see like crystal ligand splitting theory and those kinds of things and how you can apply them, because it actually does kind of pile on each other, and that's really helpful because to kind of like spot the trend and then be able to then apply that, especially in an exam, and because your exam is next week. So hopefully we can get that going. So without further ado, the one thing I want to point out is that the shapes that you guys are looking at are all going to be equivalent to coordination, and the coordination is just saying how many ligands are coordinated to the center. And then a lot of people are asking me, well, then why isn't a complex that has brackets and say it has like a chlorine atom on the outside or something of the like not coordinated to the center? And the reason for that is that chlorine or that fluorine or that O2 on the outside is not coordinated to the center, but it's coordinated to the complex inside those brackets. And inside those brackets is its own individual complex that has ligands specifically coordinating to the central atom. And then, because the overall charge is not equal to 0, it looks for spectator ligands to then adhere to that center, or to adhere to that central complex, but not to the central atom. So that is why there's spectator ions, and then there's the actual complex. And the actual complex is going to have ligands that are then coordinated to a center. And because those ligands are coordinated to a center, that central atom will have a coordination number that responds to how many ligands it's coordinated to. So email me if that explanation did not make sense, but that is where we're getting coordination number from. And so then I'm going to go through quickly some problems here. So we're wondering what's the coordination number of the ion, which we're always looking at the central one, which is the chromium, diammonium, dichloride, bromine. And then what's the oxidation number? So the chromium first is going to have these 2 ammonium ligands, and then it has 2 chloride ligands and 1 bromine ligand. Cool. All right, so they're all monodentate, and that means that there's only one bond that these electrons are being contributed to the central atom. And then I noticed that means there's 5 coordinate bonds because they're only contributing to one bond. I count 2 plus 2 plus 1 is 5. So that makes sense to me, and that means the coordination number would be 5. Now, I'm looking at oxidation number, and since the total charge is 2 minus, what I'm overall saying is that the 2 minus charge is going to equal to the charge of the chromium plus 2 times the charge of the ammonium plus 2 times the charge on the chlorine plus the charge on bromine. Now, ammonium is neutral overall, and then chlorine and bromine are -1. All the halogens are -1. That means all of your ligands have an overall charge of -3, and that -2 comes from the overall is going to equal -3 plus the charge on chromium. Cool. So then that would mean chromium has a charge of +1, and that's really unusual for chromium, and that means I would definitely not be making it in my own lab. Now, another problem that I'm too big for is the coordination number of cobalt in this complex. And the reason this one's different overall is that we've got these bidentate ligands, and the bidentate ligands is when those ammoniums there are contributing twice to the center, but they're actually just one ligand. So I would say that this has one ligand, and yet it's coordinated twice. And this would mean that this overall complex is actually octahedral, even though when I look at it written, it only has four ligands, but really it's got 2 ligands that are coordinating twice. So if I count them all up, I have 2 nitrogens from one, and then I have 2 more from another, and finally I have my 2 bromines. So then if I get all together, that's 6 in total. Perfect. If I have 6, this means this has a coordination of 6. Yep, and that chlorine ion, again, outside of the brackets is just a spectator and is not coordinating to the central atom. If it were, it wouldn't make sense. So that there's the brackets indicating that this is a complex, and then that overall complex with the chlorine is becoming a salt. Okay, now I want to do the oxidation for this one as well because it might be a bit confusing. So if we look at the oxidation, I know that my actual complex has a +1 overall charge, and that's going to equal to the cobalt charge, which I don't know yet, +2 of the enantiothioamines, and then +2 of the bromine charges. Now, the ethylene diamines are going to be neutral. And then the bromine is going to be -1 because, again, it's a halogen. And so the overall are -2. And that overall -2 is going to equal, the overall ligand charge is -2 plus the cobalt charge is to equal +1. And so therefore cobalt is +3. It's a very common valence for cobalt, so I would definitely make a complex with this. I will say, please be aware of the math. So many people put -1 here because they see -2 and +1. Be aware of the math you are doing. All right. Ooh, I went back. All right, now, orbital ligand splitting theory. Orbital ligand splitting theory is a bit confusing, I think just because there's different orbital splitting in general that a lot of people get very confused. I would memorize which splitting is which, but also for me, the one thing I remember is octahedral always makes this sort of triangular shape, and tetrahedral makes an upside down triangle shape, and that upside down triangle kind of looks like a T. I don't know. Some people don't follow me on that. They're like, well, they're both pyramids, Victoria. And I'm like, I know. But this is how I remember them. And this is going to come in handy for what we're about to do, which is pretty much, I think, what's confusing a lot of you. So we're going to go through that. So I got these 4 complexes, and I'm going to get out my pen. And I noticed that all these complexes are neutral. And so that means that because they're all neutral, that these central atoms here, these metals, are going to make up the charge of the rest of the ligands to get 0. So first, water is 0 in this first complex, and this chlorine is -1 like we've said before. So I know cobalt must be +2, because again, the overall is 0. So -2 plus 0 plus 2 is going to get me 0. All right. Then I know that cobalt is in group 9 on the periodic table. You'll be given a periodic table. 9 electrons, take away +2 will equal 7. Because remember, electrons are negative. So -9 plus 2, 7 electrons. So I'm just going to fill in my orbitals that I have here. I'm going to start with the lowest first and then move to the highest. So 1, click, click. 1, there we go. 2, 3, 4, 5, 6, 7. So I noticed that there's 2 paired and 3 unpaired. Good. All right, moving on to this next complex. I'm going to have my Cn, which is -1, multiply that by 4. And then I'm going to know that my iron must be +4, because again, it has to equal 0. I know that Fe is in group 8, so I have 8 electrons. There's a +4 charge on it, so then 8 take away 4 is 4. And then I'm going to fill in my graph like before, and I notice I have 1 empty. That's totally fine. But overall, I see all unpaired. Good. Now, when I'm doing the octahedrals, they are going to have to take into account weak and strong field, unlike my tetrahedral. Because tetrahedrals are mostly high spin, but you'll find that octahedrals are not. They can be high or low spin. So my Cn is a strong field ligand. And a strong field ligand can then influence how the electrons pack. So I have this -1 times 6, and I know cobalt is +3 because cobalt's in group 9. So 9 minus 6 is 3. And then I know that since it's a strong field ligand, it can make those electrons force together. So when I fill in my splitting diagram, they are all going to pack together because it is a strong field ligand can force those electrons together. But that's very different from this other one. Now I've got water and chlorine, and these are weak field ligands. So first I'm going to say that I have H2O, and H2O is 0, so 0 times 4 is 0, and chlorine is -1 times 2, so Fe is going to be +2, and in group 8 that means I've got 6 electrons to fill. So they're not strong enough to force together. So when I fill in my orbital chart here, I could just go 1, 2, 3, 4, 5, and 6, and notice that I only have 1 paired here, and then the rest are all unpaired. Over here, I notice that overall they are paired together, and then over here they're all unpaired. And this actually relates to which one is going to have greater splitting. This one's going to have greater splitting because they're all unpaired. The same over here, we've got more unpaired than over here. Now, this also makes sense for color. Something that has all paired electrons is then going to be very clear in in color. So I've shown it as a clear box. Something that has a few paired and some unpaired is then going to be only slightly colored. So when I look up here at this one, it's only slightly colored because there is some unpaired and some paired together. Now, the more unpaired I get, the darker the color is. So now I only have one group that's paired together, so I see the color got darker. And then finally, I have all unpaired, and this means it's going to be very dark in color. So that's my final one. And this also relates to magnetism. So those that have all paired are going to be diamagnetic, and this one up here that's all unpaired is then going to be paramagnetic. So paired is diamagnetic, unpaired is paramagnetic, and paramagnetic means it's going to give off an overall magnetism. So if I apply a magnet to those, then it's going to work. So needless to say, what I was talking about is that you need to be aware that unpaired electrons are going to be paramagnetic, and then paired electrons are going to be diamagnetic. And so, based on that, it means that when you are working through these, the more unpaired electrons you get, the more magnetic it's going to be, and the more paired electrons you get, the more not magnetic or diamagnetic it's going to be. All right, and then finally I wanted to talk about bidentate and tridentate ligands. And basically, this is talking about how many electrons it's giving. And a tridentate ligand will be able to give 2 electrons to the central atom, but that's 3 times. So it can do it 3 times that. But you don't count them as 2 electrons. Because 2 electrons make a bond. And so you count them as 1 electron is staying with the ligand and 1 is staying on the central to make up the octet. And then bidentate can do that 2 times. However, the ones that are very likely to do this are electronegative, but cannot be super electronegative, because these super electronegative ones are just going to steal all the electrons anyway. And they will not work as great bidentate or tridentate ligands, because they're going to try and break off to make their own complex. But oxygen and nitrogen are very good tridentate and bidentate ligands to help you with your homework. And to say the least, if you have 3 of them, then you're most likely going to be able to do this 3 times. So if I have 3 oxygens, I'm most likely going to be able to make a tridentate ligand. Same as if I have 2 nitrogens, then I'm going to be able to make a bidentate ligand. So for your exam next week, I've asked you all to answer a forum. Let me know if you can't get into that forum. I'm also going to send out an email later today, but overall, let me know what you would like me to do for your review next week, and we will do it. All right, good luck, guys. I hope this was helpful.